Hi guys, in this video we will be understanding electromagnetic induction. But before getting into electromagnetic induction, I feel that it's very much essential for us to understand a bit of magnet. Alright. So to begin with, now this is the magnet. This is the north pole of magnet. This is the south pole of magnet. These are the lines of force which are coming out from north pole and getting into south pole and then coming this way. Alright, so these are all lines of forces coming out from north pole and moving into south pole, and from south to north coming back again and completing the circuit. Alright, so this is how it is. Now, when we come to north pole or south pole, the focus of magnetism is over here. Now this is called as pole strength. This is known as pole strength and normally designated by small m. Alright, or we also designate it by Q subscript m. Alright, and north pole, so this is pole strength and this is pole strength. This is pole strength of north pole and this is pole strength of south pole. Now, north pole is assigned as positive and south pole is assigned as negative. I have made a small mnemonic just to not to get confused between positive and negative, and that is south negative, north positive. Alright, so south negative, north positive. Just a small bit of mnemonic to keep it in mind, to not to get confused. Now, why is it so very much essential? It's very much essential because lines of force always begin from positive pole and end into south pole, whether it be magnet or whether it be charge. Alright, even in case of charge, we would find that always the charge lines of force would be coming out from positive side. Alright, from the positive charge. Alright, here in this case from the positive pole. Alright, so these are all lines of force. Number of lines of force are known as flux. Unit of flux is Weber and it is represented by phi. Alright, now what is the significance of flux? Now the significance of flux is down here. Now when we see over here, now see this is a magnet which has got lots of lines of force. Alright, lots of lines of force coming out from north moving into south. Whereas in this magnet there are few lines of force. So if I take a material which has area A and this also is the same material which has area A, so lines of forces passing through this area is much more than lines of force passing via this area. Both the areas are same, I again repeat. Now this is what is called as magnetic field. So the magnetic field is more over here and magnetic field is less over here. So magnetic field B1 is greater than B2. Now who's responsible for that? It is flux. So there has to be some formula for magnetic field. So these are lines of forces. These are all lines of forces. So magnetic field B is equal to flux over area. That is flux lines of force divided by area. Lines of force divided by area. So obviously in both the cases the denominator is the same, but flux lines of force is more. So B1 is greater than B2. So we got a reason why B1 is greater than B2. So this is what is its formula, flux over area. Unit of flux is Weber and area is meter square. So Weber per meter square is unit for magnetic field. Alright, and it's also known as Tesla and also Gauss. The relationship between Tesla and Gauss is Tesla is equal to 10⁴ Gauss. Alright, so we got to know about flux, we got to know about B. Now let us try and understand what is capital M. Normally it is capital M, which is magnetic dipole moment. The magnetic dipole moment is pole strength. We can take it as small m or Q subscript m into the distance. Now the distance between south and north is 2L, where obviously L is length, and so if we say 2L, that means from here to here it would be L, and from the midpoint over here to here it would be L. Mind you, we are talking of distance between magnetic length, which is 2L. Alright. Then there is another thing called as geometric length. Geometric length is actual length of magnet. Now there is a relationship between geometric length and magnetic length. Magnetic length is 5/6 times of geometric length. Obviously, magnetic length is smaller. It is from pole strength to pole strength. That is what is magnetic length. And geometric length is the actual size of magnet. So magnetic length has to be smaller, and by how much? By 5/6 times of geometric length. Alright, so we got to know about length. Alright, now coming back to magnetic dipole moment. Magnetic dipole moment is one of the pole strength, which we can either take it as small m or q subscript m into the distance between the two, that is 2L. Alright, so it is m into 2L, or could also be qm into 2L. Alright, so this is what is the magnitude of magnetic dipole moment. Fine, now let us talk in terms of direction of magnetic dipole moment. Now, as I already mentioned, the lines of forces erupt out from positive and then get into negative, that is comes out from north and then gets into south, and in the magnet it goes from south to north. So what is the direction of magnetic dipole moment? Direction of magnetic dipole moment is from south to north. Now let's talk about its unit. Its unit is ampere meter square. That is IA. That is, the I stands for current and M stands for area. Alright. Now let's understand why is it so. Alright. Magnetic dipole moment. Magnetic dipole moment due to current loop is M is equal to IA. Now this is the situation. Now suppose current is passing through this loop. So this becomes the entire area. So what is the magnetic dipole moment for this system? I, that is the current which is flowing through the coil, and A is area that is enclosed by this loop. Alright. So coming back here. So M, magnetic dipole moment due to current loop. M is equal to IA, where I is current and A is area enclosed by loop. Alright. Now one thing I'm sure you are aware of, that via cutting lines of force we can generate electricity, and the same way from electricity we can also generate magnetism. Alright, so let's get into further query. Unit of magnetic dipole moment is ampere meter square, ampere for current and meter square for area. Alright, now what's the unit of pole strength? We didn't talk about it. Unit of pole strength, let's check out over here. Now, magnetic dipole moment we right now told is Q subscript M into 2L, and unit of this is ampere meter square, and this is Q subscript M into M. Length is in meter, so we take meter down there. So if I want unit of QM, I would be taking meter down there. So it gets into A M square upon M. So ampere meter. So ampere meter is the unit of pole strength, and for magnetic dipole moment the unit is ampere meter square. Alright, so these are certain things which we have got to always move around with whenever we are doing electromagnetic induction. Alright. Now when we are talking about magnet, let's get further into it. These are two magnets. Now this is the axis of magnet. Now in this case, this is the axis of magnet and this is the equator. From the center point, when you go perpendicular to the length of magnet, that is what is equator. All right, so now B axis, whenever we talk about B axis, now suppose this is the point where we want to find out. So from the center to the point is R. From the center to the point where we want to find B is R. And in case of equator, from the center to the point where we want to find B is R. Alright, so this is R, this is R. Alright, so the formula, B axis, and obviously this is what is axis and this is what is equator. Now B axis is mu 0 2m 4 pi r cube. M magnetic dipole moment, which is qm into 2l, or small m into 2l, and equatorial is minus mu 0 m upon 4 pi r cube. Now why is it minus? It is minus because B equatorial, the direction is opposite to M. Direction is opposite to M. We know M is what? M is from south to north. So this direction would be in the opposite direction. That's why equatorial is in the opposite direction. That's why it's negative. Alright. Another thing that you observe is here you have 2m. Here you have just simple m. So the relationship between B axis and equatorial is B axis is equal to 2 BEQ. B equatorial. So B axis is equal to twice B equatorial. Alright. Another thing if you observed is mu 0 upon 4 pi. Mu 0 upon 4 pi. Mu 0 upon 4 pi is the proportionality constant in case of magnetism. Whenever we are talking about electrostatic, the proportionality constant is 1 upon 4 pi epsilon naught. Let's just recap what all we studied. To begin with, we saw lines of force called as flux. Unit of flux was Weber. Then we saw pole strength, where actual strength of magnet lies, which was represented by small m or q subscript m. Alright, and then we also studied about magnetic length, which was the distance between the two pole strengths, which was 2L. Alright, then we talked about geometric length and magnetic length. We found that geometric length was 6 by 5 times of magnetic length. Then we talked about magnetic field B, which was flux over area, Weber per meter square, Tesla. Alright, this is what we saw, and we also understood how B1 was greater than B2. Then we also saw magnetic dipole moment, which was m into 2L or qm into 2L. And the direction also was from south to north, and then unit was ampere meter square. How it got ampere meter square? Via IA, current into ampere, that we saw over here. Alright, and then we saw also unit of pole strength. Now how we m is equal to qm into 2L, where L was meter. This meter we took down over here to get unit for qm, so it became ampere meter over here. 1 meter gets cancelled and we got this. So these are all that we have studied, and we have got to carry these things all the time with us while we are doing EMI. Alright, then yet another thing that we saw, which I forgot to mention, we also saw B axis and B equator, and we also saw the relationship between B axis and B equator. Alright, so guys, keep these things in mind and move forward.